think only an engineer can call a PCB beautiful. Design for the application. Don't design for what you're dreaming, which sometimes I get caught in.
I think all engineers get caught in that.
Don't try and use every microprocessor out there.
Absolutely.
You try to keep to your ecosystem.
We want to meet the minimum specifications in the minimum time and cost, and then we want to refine from there. And the long way is the easy way.
Ironically, to do something quick is to take your time. Waste that initial month or two.
Invest, not waste.
Yeah, invest.
Hi and welcome to the Engineering Triangle, our podcast about making the best smart machines and IoT as fast as possible. I'm your host, Ayrton here at Element Engineering Australia. Today is all about electronics design, covering the tools we use like Altium, as well as best practices in our experience. I'm here with Xarion Comoretto, an experienced electronics engineer who's heading up our embedded team here at Element. Thanks for coming on.
Yes, thank you.
Good. Yeah, electronics design is kind of my second engineering wind, so to speak. I started off in mechanical, but having all the data acquisition, data logging background, started to make my own circuit boards sort of 2010, 2012 from the Arduino ecosystem, getting to the limitations of the different Arduinos and then making my own circuit boards using those chips. I think over the years, I've done probably 5 to 10 years of hardcore work on electronics, and I'm by no means an expert, but I think I'm pretty good in some aspects. Good analog design and RF. But electronics is such a massive, broad area.
So unlike you, I started from the other side, which is the even more basic things. So starting with logic PCB design, rather than starting from a Raspberry Pi, which already has everything built in.
Yeah.
My fundamentals were starting basics. So designing a little counter using logic, shift gates and AND gates and OR gates, and that was my introduction into the electronics world. And then naturally it has to do more. You can't just be counting. And then program some code and do some more complicated designs.
Yeah, I think I was a bit later than you. So I started, going back even further, started with the Dick Smith electronics thing. So Dick Smith is an Australian brand. He was had like a shop like the J-Cars or Ultronics now. And you go down and you buy your resistors and stuff. And they had this like 1, 2, and 3 book where you basically have this scrapbook, and then you get these little plastic layout things, kind of like a proto board. And then you would screw in and then put your little resistors and LEDs.
You've got a reference design that you have to follow.
So the first one was like a flasher, and using a transistor and whatnot.
Some of those circuits you still use.
Absolutely,
if you don't need to have a microprocessor. Like to do a flashing LED.
Yeah, absolutely.
Yeah, you still use many of those.
555 timer counters or something like that.
Yeah, exactly.
But those things are, I think the reason why I actually wanted to go into electronics engineering at university, but I couldn't. I've always been mechanically background, and I couldn't see the applications for it. I didn't know what the applications were. So when I went to university, I saw the mechatronics engineering degree, and back then people were like, "Oh, no one's going to ever use mechatronics. It's going to be mechanical or electronics."
Yeah, you decide which one you want to do.
But now it's like, if you're doing purely mechanical, you're kind of missing out on a few things, especially with the way the world's going. So I've got into electronics and then some firmware, more web software sort of based stuff, just through my own needs and the engineering needs that we've had as part of the business to try and do smart things. And I love it. I honestly love it. But it is a real skill and a real art to doing it well.
I almost didn't have a choice to get into electronics. My father's an electrical engineer. I mean, he didn't force me into it, but he persuaded me pretty strongly to follow his steps, and it was really good. I had all the tools. I didn't have to go and buy components from J-Car or wherever it is. If I wanted to try something, we used to have those books of application notes. Get the application note, go find the component in all the little drawers. You had thousands of drawers of components and logic gates and everything, and figure out what you want to do. We also were making our own PCBs at the time. So the whole process of doing negatives and positives, exposing them, etching them away with the chemicals.
This is your family business back in South Africa.
Exactly. So, the company was, it's over 40 years old, and its roots were designing customized projects for people.
Similar to what we're doing here.
Exactly. But we were doing pretty much everything from the actual PCB manufacturing, the assembly, the code, and turnkey.
That's amazing. Yeah. I've got a different cup today. Kid's handprint cup.
That's cool. No more Mount Rushmore.
Start off with what makes for really good electronics design. Any great examples stand out to you from your own experience?
Electrical projects that were designed for the purpose are the ones that stand out.
Yep.
And of course, the ones that you actually see in the field working. It's a feather in your cap. You go walk around and you see a device that you've designed that somebody's actually using.
Yeah.
Your idea. I find that if you limit yourself to just designing in our space, in the IoT space, is that if you limit yourself to designing something just for one purpose, you end up really constricting yourself into a very small market. Because very often the IoT products can migrate to not be IoT. It can be used for something that's completely different. And you change the software using all the building blocks of what you have, and it becomes a completely new product.
So when we're saying IoT, so we're sort of saying Internet of Things, and usually the electronics domain is usually at the core of it is a microcontroller. Microcontroller is basically a very small computer, probably equivalent to 1990s PC, something like that. But it can do a massive range of different things. And each one of those pins, so it might have 32 pins, it could have 144 pins, some of them have 256 pins or whatever. Each one of those pins can usually be used in multiple different ways. So, IoT for me has been a lot about sensing and automation in an embedded way, not in a PLC way.
Absolutely.
And when we say embedded, it's this microcontroller senses the exact electrical signals in real time, like super, super high speed. Those pins can be configured to do those things, interface with those sensors and actuators, or interface with communications channels that are going to other chips that might be doing things externally, or doing communication with a computer or an app or things like that. Electronics, I know what you're saying, because when I first started getting into electronics to do my own little data loggers, we had to figure out the hard way. I was figuring out the hard way how to use these chips. And you usually end up finding bugs or gaps in the data sheet where there's an errata, 1,000 pages later or something like that. And you go through it the hard way. But we kind of leave ourselves the opportunity now to understand what this thing's capable of and try to give ourselves the best opportunity to conquer one thing, but then easily iterate on that same process.
You also have to stop yourself, because you can't just carry on designing you want it to do everything. You have to, put the ceiling to say, we can't just keep on designing. Make it as flexible as you think that would get.
Within a certain amount of time and cost.
Dream a little bit, but don't go too far. Don't limit yourself, but don't go too far.
So some commercial products that I've worked on here would be ShockWiz, TireWiz. We've got our CUDA dairy hydrotune now. ShockWiz, I was really ingrained in that. It was pretty simple, pretty simple device. I would say we had some good input from a number of different people, and it came out to be a product that we've never really had to change. We've never had problems with on the production line. It seems like it's gone pretty well. So I would say that's a fairly successful product in itself. TireWiz was one that was a lot harder, because we didn't use a Bluetooth module that had its own antenna and things like that in there. So we had to actually put the tiny little 0.3 mil BGA, Nordic NRF.
You're going chipset level, basically.
Chipset level, and then because we had only a certain circuit board thickness that we were allowed to use, then the RF traces became quite challenging. So that board was heavily refined, number of iterations.
And in RF, they actually say the first thing you should do in a PCB design is put your antenna down.
Absolutely.
First.
Don't
start fitting all the other electronics and the antenna becomes an afterthought. The antenna is the most critical thing in an RF circuit. So start with that, make sure you nail that design down, get the reference design, and then work backwards.
And we did that really badly as well, because we had a constraint where the components on the circuit board needed to be on the underside, but the antenna needed to be on the upper side.
To change.
Because we've got a rim there, aluminium rim or a carbon rim that's going to attenuate your signal. With the antenna being directional, and on the underside it would have had terrible radiation properties.
So it's really close to the metal.
Basically. So we had to put it on the top, which means that we have to have a via, and then that's a no for for RF. You can do it, but you've got to characterize it. So we did. So
then you eventually have to match it, and you have to go through the whole.
And we did. So we had to do the correct antenna routing design for the thin circuit board, multi-layer, 6 or 4 layer, I can't remember, circuit board that we had, match it with using all of the VNA equipment that we've got here. So that was quite a fun one.
It's amazing changing, 0.6 millimeters, like it changes everything.
Absolutely. But that's probably the best one I can think of for myself. You've done a lot more commercial products than I've done. What would you say is a good?
I find good designs are also designs that your peers can understand.
Yeah,
so
absolutely.
If you're designing it and you're in your own little space, as soon as you hand that work to somebody, and I speak from experience, you have to design it for other people to take over.
Yeah, absolutely.
Have the right comments, have the right structure, how things are laid out.
How you lay out the schematics.
Don't just bang something out for the sake of getting it done quickly. There's a longer vision. If somebody has to take it over or somebody else wants to do some modifications, they have to know what's going on.
It's collaboration, true collaboration, right?
Absolutely.
Good engineering really comes down to communication with others. And if you're doing it by yourself, then unless you're going to do the whole project from start to finish, you've got to do things in a way that are communicable to other people. So.
And of course, the version control, just to know what's going on, know the history, why were certain decisions made, because that gets lost in translation. You know, as you work with different employees, that information doesn't translate to the next one. So just getting everything down is so important to having a solid design.
Yep. Have we got a schematic sheet inside of this Cranio where we can show sort of the notes that we create?
Absolutely. So a top level schematic design is where everything is designed in blocks. So that you can have a view of the whole system. And then each block, once you go into it, you can see exactly what is going on. So for example, we've got sheets on the left-hand side here, and we can see up to 14 different sheets of the schematic, which breaks up all these little green building blocks, essentially. We can see here it says microcontroller, PWM outputs, analog outputs. So each one of these is referencing to
another sheet.
Its own sheet. Absolutely. It's much easier to view in its own space instead of trying to cram everything into one page. Having wires, running up and down and left and right. Just break it up. If you're looking for something, it's easy to know. Go back to the top level, scroll around, find whatever you want to talk to, and break up the work. And you can see how they interface to each other, which is also really important for when you hand it to the software guys, because the PCB design is only the beginning.
Yeah, absolutely. So if we go back to the analog input schematic, and the top corner, that note there, we do a lot of these in our schematics, is where we are basically putting down the information
the notes, just some notes, absolutely.
Yeah, basically trying to specify what we did, because I looked at one of them the other day for a client, an old client that we were doing some new work for, and we didn't have some of these in the sheets. And I had to go back in and look at the circuit and say, okay, that's a 10K resistor on that configuration pin, which then is current limiting to 3.6 amps or whatever. But I had to go and reverse engineer that, which is time and cost to the
if you just put a little note, like I even see there's a circuit simulation, why were certain values decided upon. I mean, there was a circuit simulation, and it's there.
These are clean. These are a lot cleaner than I think I've ever done back in the day.
If I have to think where I started, it was... and I think it's having a bit of pride of work. It's very easy just to throw something together and it's going to work, but it's having pride in your work as well.
Another thing with electronics that's a key conundrum, I think, different to the mechanical space, and I think definitely different to software space, is if there's something wrong on that board, it's going to take you 6 to 12 weeks to figure out that it's wrong. Because you need to go and make a new circuit board, invest in those chips and someone placing components on the board. You then have to get it back. You then have to do the smoke test, see what's going to burn out, fix things.
Well, you still have to send it to the firmware guys. The firmware guys have to go back to the hardware guys. You have to figure out, is it a firmware problem or is it a hardware problem?
Is it an electronics manufacturing problem? A bad solder joint or something like that. So these nicely refined schematic sheets have actually been nicely refined over a number of different iterations. But it's not a fast turnaround. With software in the web world, if something doesn't run, it doesn't build. And then you go back in and you go, oh, that's where I change it, bang, done. You know what I mean? Electronics is the exact opposite, and it has a massive lead time.
You have to do the full process to get it on your table, assemble all the components, apply power.
And the other part as well is you could be simulating this on a proto board or something like that. True. But when you actually place that into the circuit board, it has other complexities. So, the actual physical layout, the soldering, they're not big complexities, but they are an extra complexity.
Like there's always pride in your work. So don't just put the components everywhere.
Yeah.
There are some beautiful designs. If you can, I think only an engineer can call a PCB beautiful. But
well, bring up a beautiful PCB. I don't know if this one is beautiful or not, but
no, absolutely.
It looks beautiful. There you go.
Yeah. So in your previous podcast, you were speaking that you're starting in 2D essentially.
Yeah.
PCB design has been very much that.
Yeah.
But now you've thrown together a lot of other things. You can bring in the 3D shapes of your enclosure. You can put the 3D shapes of the components. You can literally have everything in one place, and it gives you exactly what it's going to look like when it comes back.
Yep.
You have your enclosure. You can make sure all your keep outs. For example, this green part is the aluminium
housing.
Yeah.
Can you go to the 2D view and just show us like the routing? So this to a mechanical engineer would be like, what the hell is that? That's a bloody mess. And it is.
My wife calls this the traffic jam because whenever I'm moving components around, it's like if you think of that game where you're moving the cars.
No, I don't know.
Rush Hour. It's called Rush Hour.
Yeah.
So you can spend hours just trying to have a good PCB design just because one component doesn't fit there.
I remember some of my first data loggers in a Deutsch box or whatever with BGAs where you're using nearly every pin and you'd fan everything out, you'd place everything, and then you start routing it. You're out 80% of the way there, and there's just no physical way of you getting through. And you go, oh, what am I going to do? I've got to reroute everything, or I'm going to add more layers, and I'm going to add more complexity. Yeah.
But the other thing is that then you think of an idea and say, what if this thing could do that?
Yes.
And it's that pin that's right in the middle. And to access that thing, you got to shift everything away and try and get that one out. But it's a puzzle.
So there's lots of stuff going on there. But
so
there's methods to the madness.
This is an 8-layer PCB.
So we've got 2 ground planes, 2 power planes, and 4.
And of course, the stack up is always important as well. You have to make sure which you choose to be your power, which to be your ground.
And that's usually given by who you're going to get to manufacture the circuit board.
And of course, you have to think of EMI eventually, different certifications. It's all related to how many layers that you need to use. No longer are you fixed by the constraints of double layer. The price increase to go to 4-layer, it's not double the cost of a 2-layer. It's just become a normal practice to not do a double layer.
Yeah. I think for me it was 4 layers because of the cost is very minimal. It's so much easier to route a 4-layer than it is to route a 2-layer.
Yeah, you can have a good ground, you can have a good power. You don't have to compromise all your tracks to try and go around power. Like you can dedicate one for signal, one for power, one for ground.
And just pay the $2.
Just pay the extra, and you're going to have something solid, good heat dissipation. I find there's always a trade-off if you're trying to stick to 2 layers. And you're changing layers all the time, whereas just change once, leave it there, and use another layer for power.
Some of the more complex boards, so some of my early data loggers were sort of 10 layers with BGAs and just everything mashed on there. I found that having the top and the bottom layer, you're basically just using that space to position the components and get your traces out, basically, to a spot. Then you were veering down. And then I would have certain layers which would go vertically, certain layers that would go horizontally, and then you would end up creating patterns where if you absolutely necessarily needed to, you could go from your pad, go down to the next layer, go vertically, then go down to the next layer, go horizontally, then come back up or whatever. It's not the best for EMI and all that type of stuff, but if you really need to have those high-density interconnect boards, you can do things like that.
Of course, if you've got complementary pairs as well, it's a lot easier just to do it on its own layer instead of going in and out of other stuff, avoiding other things and then trying to get them the same length. It's standard practice now to do multi-layer.
Yeah, for sure. What about bad design?
Well, bad design is some of the designs that I've done. Absolutely.
I think we've all done bad designs.
And it's when you think you're God's gift to the electronic industry and you think that you'll get this thing right first time. And you just go to do the schematic, do the PCB, and you're so confident, send the PCB to be made, and then it comes back and you've missed the programming header. The important part is actually to have a review. Someone to review your things. You're not the best in the world. Just go through the process.
We have an engineering sheet we go through now to make sure that we've ticked everything off and we've hit all the marks. I've had a lot of bad designs that something was wrong either in my circuit board or in my schematic. And when you first fire that board up, it's red hot. Something's burning out. Yeah. How do you do the smoke test? Because I know every electronics person that I've worked with or talked with, they do the smoke test. You got to try and keep the magic smoke in. One of the things you're trying to do is effectively for that first board that you've got the golden prototype, it's cost you a lot of money and a lot of time. So even if there is something that's burning out on it, you got to get that thing off the board and then save the rest of the board so that you can continue to pass that on to firmware team so they can basically do whatever they need to do on there, and you can continue with refining your board in parallel.
In my experience in the old days, there was no link between the schematic and the PCB.
Right.
So you design your schematic and then you design the PCB.
Right.
And there was no cross-referencing. So that's where I found the most smoke came out, because you have to go through a whole design process, go through each pin, go to the data sheet, make sure it's correct, and there's no cross-linking. Now you can't actually connect a wrong pin unless you've designed the component wrong. So I think that how often the smoke comes out is a lot less now. Just because you're absolutely sure that you've created the component correctly. What can happen is that maybe it's a mechanical thing. Maybe there's a solder blob or too little solder, or there's no ground to dissipate the heat. That's where I find that the smoke comes up. But an easy way to get around it is first time you apply power, just current limit your power supply to something that can't blow. And if you see it's shooting up, switch off, and then drill down and see what area is it.
How do you do that? Because I used to do that with my fingers.
Depends how fast it happens. But I find sometimes when you design circuits, connecting power to different portions, you use like a 0 ohm. So you can isolate different ones.
Zero ohming was a hard lesson I learned. Zero ohming the power rail of a subsystem to then be able to just turn things on by soldering this 0 ohm resistor in place.
And I find if you're designing, if it's your first iteration of this product that you're going to design, don't already try and fit it in the enclosure. Design all the components, make it as big. Do so that you can do all of your current tests, you can do all your functional tests.
And then miniaturize later.
And then scale it down, because you lose a lot of time. And when you make something small, there's a lot of extra work that's not necessary, and you compromise a lot of things by trying to make it small and trying to get these things in and out. Your first iteration should be a functional thing. Make sure that the proof of concept is going to work.
So previously we used to do, I used to call them Franken boxes. So you get, and we're very lucky these days. And I think that's what makes it easier to get into the system is the likes of SparkFun, DF Robot. What's the one in New York City? They're very big. Adafruit, they're fantastic. And having these little demo boards that you basically wire together with hookup wire. You would then have a proto board with your own particular little tiny circuit that is specific to you, and you can do most of your work there. The second stage
just looks horrible, but I mean,
but it works, right? And I've seen some products go to market that are literally just that.
It's just easier.
Proto boards that are put onto a little carrier board or something like that. The next stage would be to basically grab those things and put it into a proto board.
I think it all depends on the scale. How many are you going to make eventually? If you're making 50, just use something that's already built.
So
but if you're doing thousands, there's a big cost saving in taking whatever is on that little board. Putting it on your own.
So you're not paying for someone else's profit margin by having their piece. But it's horses for courses. But I totally agree. One of the things that where the smoke came out for me was wrong pins on the chip element, on the actual chip itself. So you've got the schematic is probably right, but then the pins are the wrong position on the package or something like that. Like SOT23 transistors that can be different.
And when you're designing the component, sometimes look very carefully at the package, because the pin's actual design looks the same. But the pins are different.
Exactly.
And it'll look like a SOT, but it's a UFN. And you've just assumed.
You're giving me nightmares. I'm getting flashbacks.
And you just assume that they would have used the same pin out.
Absolutely. That's what I did with one of my first little data logger designs. And I got it manufactured by a company over in Adelaide. and they called me and they're like, "Oh, we don't think this one's right.
This footprint doesn't look correct."
And I was like, "Oh, I just fit it." And then you get it back, you put it in, the smoke comes out, you save the board, you pull those things off, and then in that particular case, I was able to just turn it like 120 degrees and get it to work.
It was a 3-pin device?
3-pin device, just turn it. It was magic, but otherwise you'd have to turn it upside down and bend some legs. Or wire modding is nearly always done, right? We have had quite good success lately where the boards that come out have been
they've been very good.
From one.
It's gone through 3 people by the time you've made the board.
Yeah, but wire modding is something that people shouldn't be afraid of or be embarrassed about in any way. Wire modding is a commonly done thing. So you've got a circuit board that you spent months and hopefully not months, but weeks and months on, and you've got it back and some smoke's come out. Wire mod it so you're bypassing something and making it work, because getting that board to work even partially is going to have give you a massive...
You'll find a lot of wire mods in a lot of Wi-Fi routers, and I mean, sometimes you open things and you're like,
this has gone to production and this is sold in the big box store.
And they're doing thousands, not tens.
So I won't be so embarrassed.
It happens everywhere.
What software and tools do you use for electronics design, and why?
I think this all relates to, like, our first point is that electronic design can't be in a vacuum. Like, you can't just work on PCBs and schematics. You have to know, what can this device actually do? What can those pins be used for? Microcontrollers now, you can move things around. If you don't want the UART on this side, you can easily put it to that side. And what you find is that you want your tracks to run nicely. So you end up going backwards. You've already designed everything. You say, well, if I can just move these 2 pins a little bit further up, they're going to run really nicely down there. It doesn't matter, because this is a GPIO, that's another GPIO. And it just looks much, much nicer rather than jumping over, changing layers. So when we design something, we always have the IDE, whether it's an MPLAB code generator or if it's an ST device, we've got the CubeMX. It gives you the layout of the pins, tells you what functions those pins can do. And it's really easy then just to translate that to the schematic and then run the pins.
So you're mechanically looking at what the size of the product might be, where the subsystems may be placed for the mechanical interaction, electrophysical interaction. Then basically going and using the IDE. So it's this coding environment.
So there's 4 pieces of software. So for Element, there's the mechanical side. So you've got the SOLIDWORKS. That SOLIDWORKS you bring into the CAD as we showed earlier. So that you know where you can't put components, so that they don't interfere with whatever's is going on the enclosure.
And that's in Altium for us.
SOLIDWORKS is the CAD side. Altium does the PCB design. Then you've got the IDE, which does the software. And
so that's usually the firmware coding interface. So that's for Atmel and Microchip. We're using.
You've got the MPLAB, or I mean, everything's going to, even VS Code now has your code generators. That's also useful for the electronics guys, just to write quick software just to make sure that the electronics is working. And then it can be passed to the firmware guys.
Integrate it.
Into the full integration. At least the electronics guys can tick everything off and say, my side is working. We're happy with it.
So there's 3 major tools there. The other one would be, so once we're in Altium and we're designing schematics, we're always working within the data sheets available from the different suppliers. Some of those data sheets can be 10 pages long. For a microcontroller, it can be, and I'm not kidding here, thousands of pages long. I think the Atmel M7 high-speed microcontroller that we use in a lot of our designs is about 3,000 pages long. And
this is a good shortcut, not having to go through all of that. And sometimes it's really difficult to understand. There's a lot of information in those data sheets. Whereas the IDE, it's a simple click. It tells you what that pin is allowed to do. And then it's easy.
So we use the IDE, and then we're getting the different pins and stuff like that. Once we're into a schematic and we're bringing in other components or different subsystems, a lot of the time we're doing circuit simulation. We seem to be using sort of open source tools these days to do a lot of the quick
basic.
They're fantastic tools to be.
They're good just to know little RC circuits and timing and even
digital switches and stuff.
Even filters. Filters, getting a sweep of your frequency, get the response. It's really so easy to do now.
And then, so what is there any other tools? So once you're in there, you're making the schematic, where obviously then laying out the circuit board. We're going to lay out the critical critical traces first. So antennas first.
I think what you have to do is put everything down where you would like it to be. So if it's an RF, start with the antenna. Always start with the antenna. If it's a PCB antenna, if it's one that's on a UFL, then you probably got a bit more sort of flexibility. And you have to lay out where you want your connectors because the connectors cannot not be there. You know where the connectors go, so put them down, put the major components, and before you start connecting tracks, just lay everything down. It looks like an absolute mess. Before you've run the tracks. It just looks like a spider's web. And to someone that doesn't know what's going on, it looks horrific. But in your own mind, when you've already have the end design in your head, you know exactly how everything connects. And then you'll find it'll be backwards and forwards because in order to run this track better, then it'd be better if I use that pin on the micro. There's a bit of backwards and forwards.
So we're starting to do that. I guess once we get a circuit board working, the tools we would use would obviously use an oscilloscope and things like that to be probing in.
Very often these days, because you can link the schematic to the PCB, the actual oscilloscope work is much less. Unless you're decoding some weird protocol and making sure that your TTL levels are right. But these days it's
less of that.
You're using applications that's already been designed, recommended application circuits. You know exactly the components they've given you, even the manufacturer of the component. So you know that it's going to work.
Should work. As long as they place that component.
But very often, if things don't work, then you'll find it might actually be a mechanical problem because the one pin of the microprocessor didn't have enough solder in the prototype. And you spent your whole day trying to find a problem in code. Meanwhile, if you looked a little bit closer, you'll see that leg is dry.
So having a microscope, a good microscope.
Microscope is actually a very useful tool, and they're so cheap now.
Absolutely.
A high-res thing goes onto a screen.
I see the guys all the time at Gary's workbench using the high-powered microscope, and they're zooming in and around, and then even soldering directly underneath them. It feels weird to me. I've done a lot of soldering.
I can't solder through a microscope.
No, but these guys can. It's pretty cool. But there's an array of many more electronics tools. But I guess our tool chain is probably pretty similar to most.
You also try and keep. You don't try and use every microprocessor out there.
Absolutely.
You try to keep to your ecosystem. You've got all the development tools. You've got all your code that you've written before that you can reuse. Building blocks. Just because someone's brought out a new microprocessor.
I hate that. That's my absolute hate is when the latest and greatest thing comes out and an engineer goes, I want to use this one. It's like, no, do not touch that thing because there's 6 months of sunk work that needs to go into changing microprocessor to update the code or whatever to get that thing running. We've been down that path many a time.
Unfortunately, it becomes a personal decision because sometimes when you have an engineer that really wants to do that, then you want to believe in them.
If they take ownership, then I'm all for it. Total ownership of getting that thing across the line.
But we've got experience, and sometimes the experience should trump what
you would hope so. But no,
so.
It's definitely again the engineering triangle. We've got it back on the desk now. Time, cost, and how good it is. If it's really, really awesome, but it takes a load more time, which is then going to impart cost, then for the business or for that project, it may not be the best thing. But if that chipset gives a massive functional change that then decreases or even enables.
Make sure you really need it. Don't just use it because it's new.
So one of my favorite sayings that I like to tell everyone with electronics is, and I don't know this for sure, this is my own hypothesis, every chip has a bug. And I've come across it a number of times with different microcontrollers that I've used, even accelerometers. So the first shock whiz that we had, the accelerometer that went in there had a very well documented in a 100 or 200 page data sheet. There was one line that says you must, if you're depowering that accelerometer, you must take that voltage all the way to 0. Otherwise, if you repower it, it won't wake up. Right. Okay. And so there's not an errata or anything like that. It's just one sentence. And we missed that. So we didn't have like a pull down resistor on one of these pins, which obviously you don't want to use.
Still kept some voltage on the pin.
Yeah. So if you pulled the battery out of the shock whiz on these P5 versions, and put it back in. You were fast at replacing it within 30 seconds. The thing wouldn't start up.
Oh.
Yeah, couldn't power up. So that is a classic case of every chip has a bug. It's in the data sheet, but someone has to explicitly see that and then put that component into the reference design or whatever. You could see as a battery-powered design, that's a bad design choice to have a pull-down resistor on, say, the power supply.
Absolutely.
Because you got a 1 mega ohm draw.
It's drawing power.
Yeah, exactly.
All the time.
So that's just one example. Another example is my first little converged, we call them converged, which was a highly condensed data logger for the trucks, mining trucks. I had everything under the sun on there, and I had a very fast, it was like a 200 megahertz microcontroller, and I used every pin. It was a BGA. And the I2C bus on that particular variant had a very odd bug, and we could never get I think it was the IMU that we were using, which was running off I2C because it was the last pins that I could use. I should have used SPI, but I used I2C. And the errata note, or the note about it, was deep in some Altium forum. Oh. And so once you get into the depths of it and you're banging your head against the wall as to why this thing won't work for months, and you're spending weeks or months, and that's cost and time, right?
Eventually, you just work the software around it to say, I can't spend any more time in this. Like
this one we couldn't. So, and what we ended up finding out was that version of the chip, the U version or whatever it was, just don't use I2C with it. Oh. So we had to redesign the whole thing around this, around a different variant of the chip. And we ended up using it. We ended up doing another spin, but it was a totally different design because it was a different version. Yeah. Every chip has a bug. So once you've got that thing working, that chip working with those known bugs in it, it's very hard to justify going to a new one which is going to have a bug.
No, you're familiar with what you're working with.
Exactly, and you're working around it, and so, or you haven't discovered it yet. Yeah. So yeah, working within the ecosystem that you've got is a massive tool to do engineering fast and good and cost effectively. And I think a lot of young engineers get caught up in the hype train. Oh, this is the latest and greatest. It's the best. Well, there's a reason why it's not been used yet, or you know
what I find is also lacking as an engineer is that if you're looking for help, you go online, you get onto the forums and you ask questions and people ask. But I think the manufacturers would actually make a lot of money if they had proper courses. If you could spend a week and have focused training on this device.
Yep.
And to avoid you spending months trying to get up to speed with whatever it is, I think people would sign up
I think they are doing that. I think Jonathan went and did the Nordic course recently. That was very good.
It's not that
common.
Yeah.
I think
they expect you to sort yourself out because there's enough information on the internet.
Yeah.
But so we don't have time to waste waiting for someone to reply. Like in a week, if we just have something focused, let's go through everything.
There's a real difference there between Australia and South Africa. Your experience in South Africa and now in Australia. I've done a lot of work with in America, and the applications engineers in America are plentiful. Even when we were doing projects for American companies here in Australia, we were still enabled to get support over there. There's all these weird things especially in the electronics industry. Electronics industry is amazing because they look so far ahead because they're trying to support people that might not have a product for 5 years, right? But as part of that, there's these agreements. So the applications engineers I've found, unfortunately, in Australia, there's a lot of engineering that we do and very little number of applications engineers. And you get minimal support. I found when we were working with America, a lot of support. And it seemed to be a lot more in-depth support as well.
They're very good at selling it.
Absolutely.
And I think that's the problem is that if you're selling it, if you want to sell it well, you actually have to know what you're doing.
Yeah.
You can sell it on specs, but once you get into it and you know exactly the trauma that your customer's going through,
it's exactly the same as the mechanical side with the SOLIDWORKS resellers and all that type of stuff. Like we're in it all day, every day. We're banging our head against the wall to try and get this thing done.
We could sell it better than them, because we know everything about
and they got limited resources, but at the end of the day, like we get through it and we do it. But we probably know as much as, or if not more than a lot of these applications engineers. And I think a challenge coming is you and I have done a lot of stuff on forums and things like that where you actively contribute and all that type of stuff. ChatGPT is taking a lot of that away, right?
That's true.
So people aren't on the forum anymore, but they're going through ChatGPT, coming up with an instant solution, but then not having the ability to contribute back. So what is it? SourceForge, I forget.
Stack Exchange?
Stack Exchange.
The
traffic's just plummeted. So I think for engineering, if you are benefiting from these open source communities or communities who are collaborating with, you've got to give back. You have to absolutely give back.
Take.
Don't take, exactly. And so even if you're using ChatGPT or any of these AI tools, if you have a solution that is to some challenge, you need to document it. Otherwise, when we go forward, we're not going to be able to see these challenges. They're going to be inside the MLs or inside the large language models, and they're going to be the ownership of the IP, or not IP, but the knowledge base. So me in particular, mechanical engineer who's had an interest in electronics, I've now taught myself, self-taught through the internet and seeing all of those challenges that people have put out there. If people don't contribute back to the environment, well, I might not have the opportunities. Yes, I'm going to be getting it from ChatGPT or whatever, but that's going to stagnate.
It comes down to effort, right? Because if you're just taking, it's really easy. But to contribute and to, go through something that somebody else is going through and walk the walk.
Absolutely, yeah. And a lot of engineers are quite introverted as well, I guess. So people, in general will take, but to give back is a big challenge. So I think as a community, we've all got to do that. And I've done it on times. I use Reddit a lot. So Reddit has a lot of high-tech pages and things like that. And I often contribute back, especially to SOLIDWORKS and things like that. But probably haven't done it enough in the past. So at this point in time, I think it's more critical than ever that we continue to share the learnings that we've got throughout the internet and keep growing the internet rather than stagnating the internet and having it all build up in the LLMs. Just my personal opinion, but yeah. How can electronics design be done quickly? So this is the big challenge, and this is something that I'm discovering, an undertone that I'm sort of getting lately from different things that we're doing. Engineering is a forever thing. Engineers can polish things. Engineers and designers can polish things forever, but the real art is, this engineering triangle is giving it an output that provides a specification in the minimum time and cost.
Draw the line.
Yeah. So for us, I guess in our electronics domain, we've been lucky to build up a wealth of knowledge over the years with all these different subsystems. Yeah. And we actively rely on those subsystems that have been tweaked. The first version of it, the smoke came out. Yep. And then the second and third version, they weren't quite hitting the mark. By the fourth version or whatever, it's pretty dialed.
Nailed down, yeah.
And then the way we kind of do it fast is we just reuse those bits of IP, drop them together into a design. We utilize our tool chain, and we know our tool chain very well. And we basically try to meet the client's minimum specifications as quickly as we possibly can.
Well, that's the beauty, is that you've done it all before.
Yeah.
You've got these building blocks that they're working circuits because you use it on this product, and you can build up a system for a client really quickly because that these subsystems all work. Take a bit from that one, bit of that one. Yeah. We've got the software for this. If we change a little bit, we can get something out really quickly.
Yeah. Engineers going into an ecosystem, just use the ecosystem as is. Don't try and change things because you might not understand it. Brownfield stuff is always harder than greenfields. Greenfields feels easy because you're learning on the job, but going into someone else's ecosystem where there's notes and things like that, put the effort in to really understand the ecosystem that's there and use what's in there, because in the long term, it's going to be beneficial. If you go and do everything from greenfields, you're probably going to run out of time and money pretty quickly if you did that every time. So how would someone these days, I guess, if they were starting from scratch or if they were coming into an ecosystem, how would they do it as quickly as possible?
It's a lot of learning because A, you have to understand the market.
Yep.
B, you have to understand the technologies. You have to understand what microprocessor you use. How long are those components going to be around for?
That's a big one.
That's another thing you have to keep in mind is the longevity of this component that you're using.
Yep.
Especially if it's specialized.
Yep.
Eventually, they're going to manufacture something newer because it's cheaper.
Yep.
And then you're stuck, having to still do that jump.
All electronic components have a certain service life or sale life. So most components that I've seen, maybe 10 years, 7 to 10 years, something like that. That latest and greatest microcontroller is going to be manufactured in a number of different versions, which are going to fix internal silicon bugs, and it's only going to be manufactured for a certain period. Through COVID, we saw a lot of those end-of-life chips get pushed forward, and we had to redo a bunch of designs for customers because chips went end-of-life.
During COVID, it was faster for you to do a redesign than to wait for that chip to be remade.
Yeah, yeah.
So there were such huge design cycles because stuff was just not available.
Yeah.
And what was available was similar.
Yeah.
So you have to redesign everything because you know that you can buy 50,000 of this IC.
Yeah. Obviously, you're going to redesign, you're going to design something with an ecosystem of components in mind. Whatever components are readily available to you and probably have the best support. And whatever that support is, and usually the support in our experience has kind of been forums or online.
And actually what's fantastic about Altium is that it's linked to all the online providers.
Yep.
So you've got the DG keys there, you've got the Mouses.
Yep.
It tells you availability. It tells you, is it recommended for new designs? Is it on its way out?
Yep.
So it's all online now.
Yeah, yeah.
Like it's linked. You know the price.
Yep. It's always been online for me, Xarion, but not for So I only got into it about 2012, 2014, you got a couple more years on me. But the other thing as well is probably the quality of the documentation. So I found myself early days using a lot of Texas Instruments stuff, especially in power management, things like that, because they had amazing online documentation. Yeah, things change. They always change. A lot of electronics companies get purchased by other electronics companies. That's a massive bugbear.
And then they just can the whole line.
Yeah, can the whole line, or they roll it in, and then the documentation is different. So working within the ecosystem that you know, and then probably coming up with suppliers that you like to work with due to availability of components, availability of support,
and the whole ecosystem thing,
documentation. Ecosystem.
You're used to how things work. The data sheets are always in the same format. You can quickly reference. You know exactly where to look.
Yeah. That's a big one.
Ironically, the other, to do something quick is to take your time, because if you've quickly rushed something to get it done quickly, and you've sent the PCB to be made, it's come back and something is wrong,
come out,
and you waste another 2 weeks. Whereas if you just spent that extra day or two, not rushing to get it done, you've actually saved yourself 2 weeks. Waste the time at the beginning. Spend extra time there. Make sure it's done right. Then send it out.
My dad always says the long way is the easy way. And you imagine, you do work on cars or whatever. It's always the same thing. It's like, if I can get to that bolt, and if I do it with this crazy weird thing, then it takes way longer than just taking off that other piece and rebleeding the cooling system or something like that.
Exactly.
Yeah.
It comes with releasing products as well.
Yeah.
Like, waste that initial month or two.
Invest, not waste.
Invest. You're going to piss off some clients to say, but you promised me this now.
Yeah.
And, releasing it prematurely actually just adds so much time at the end, because it has to come back, go through the whole design process. Piss them off and say, it's not ready. Let's get it done and do it properly, because you use less time in the end.
Yeah. So transparency of communication is probably a big key there. The way we operate here is 100% transparent. We'll tell you exactly what's going on if you want to ask. We can give you the short version, but if you really want to ask, this is the reason why. That's a big thing that we've seen, and you and I have seen recently with different clients, where they go with other suppliers a lot of the time and do some shortcuts or whatever, half spend the budget, and then come out with nothing, and then we have to pick up the pieces.
Start again.
The long way is usually the easier way or better way for the longevity of the product.
Do it properly.
Do it properly. So, but it's got to be done within reason, and it's got to be.
Don't take forever. Don't go into an endless design cycle.
Yeah. So we want to meet the minimum specifications in the minimum time and cost, and then we want to refine from there. That's the mantra of all good products businesses, which really should be just utilizing the ecosystem we've currently got, specifying the specifications, minimum specifications, get there as quickly as we possibly can with diligence, and then go and make a V1. See what smoke comes out or not, wire mod it so you're going to get a somewhat usable board in some way, delegate that to different tasks so you can do it in parallel, and then go.
And these days, it's so quick to get a PCB made. It's unbelievable.
Yeah,
like they work 24/7 there.
Yeah. A lot of it's automated as well, isn't it? It's just.
I mean, it's really interesting how they make PCBs. I mean, maybe not for everybody, but the technology of how things are stacked. I mean, the ability of having 16 layers that can all talk to each other.
Yeah.
It's
micro physical drilling, and then the laser drilling and all that type of stuff. Plating on top.
For some, it's really exciting. For others, not so much.
Electronics PCB manufacturing is a hot topic right now, because a lot of it is done, vast majority of it is done in China.
Yeah.
And with sovereign capability being a big thing, I think especially in America, they've actually put in quite a lot of funding, and it's not much, but it's more than it ever has been, just to have sovereign capability in regards to PCB manufacturing. And the same thing with manufacturing of chips and things like that. But all of those chips and things all come back to a circuit board, and most of those circuit boards are made in China.
I mean,
they do a fantastic
everybody
job.
wants to do local manufacturing, but yeah, in essence, that component is made or is in the same place.
Yeah, no negativity incurred there, but it is an art and it is commoditized. It's one of the best things that I've seen in the manufacturing world, where you can basically go online, submit your design, automatically get a quote, and that quote is hyper competitive. And you push the button, you put your credit card in, and
that's the value.
That's
it doesn't change.
And 2 weeks later, or 1.5 weeks later, whatever exactly they say, it comes through DHL and it's on your table and it's done. And they do that in an automated way. Then that night, at middle of the night, usually we get an engineering question, an EQ come back. In the morning we say, this is the change, make that change, and it's done. And that's really the way that all engineering supplier relationships should really work. It's very hard to get to that point, but I think they've done it. They've got to that point because of the commoditization. They've had to bring that cost down and rapidly be able to create these things.
I mean, just the scale helps them save a lot of costs.
Yeah. It's pretty impressive, pretty amazing.
The world is playing a bit of catch up.
Yeah, that's right. We have to. Yeah, it's good. All right, next question. What are the main constraints with electronics design? How can we do it cost effectively? Electronics, first of all, is time. So, if you're spending time on things and using the latest and greatest, or you're having to reinvent the wheel every time, that's just a bad use of time, which is cost. But the other thing as well is probably choosing the right component variant within your ecosystem that is not going to incur that high cost.
Of course, also using the right tools for the job. It kind of ties up all the other points that we spoke about today. Is know your products, know the ecosystem.
Yeah.
Because just working with something that's familiar. And not having to restart, find some library, test the library, see what this open source library forgot to do, eventually can it and start writing your own. There's all time. And time is money. So
absolutely.
Work with the right tools.
Within the ecosystem, if you've got different variants, cost effectiveness of a electronic design probably comes down to your non-recurring engineering, so your upfront engineering costs. The actual manufacturing of it long-term for a product is usually probably down to the components that you choose and your bill of materials cost, I guess. So decreasing your bill of materials cost, selecting the correct microcontroller or components within that ecosystem, not over-specifying. So if your product only needs a 1% accuracy, don't go and detail everything for a 0.1% accuracy, because that's going to cost you 10x or whatever it's going to be.
And then, of course, design for the application. Don't design for what you're dreaming, which sometimes I get caught in.
I think all engineers get caught in that.
You've got this idea that it would be really cool if you could do this.
It would be really cool. That's the bane of engineering, especially young engineers, right? Young engineers get caught up in, this is so awesome. Like if I just add this feature on, but you got to know what the specification is, and you got to know
what are you solving.
You got to know the bell curve of the end users. If that thing that you think's really cool is affecting 90% of the bell curve, okay, great, right? The center 2 standard deviations, right? If your cool idea is affecting you and 1%, is getting cut. And when refining products, the first thing to do is to delete things. And if that means, in a lot of times, if that means getting rid of 1% of the potential population, but it makes it better for time and cost and non-recurring engineering, it's got to be done.
And also, engineers want to solve 100% of the problems. You have to accept that your device will not solve 100% of the problem. But if you're solving 80% of the problem,
absolutely,
you've solved 80% of the problem.
So what is the minimum specification and what's your stretch goals? And then the product game. So this is kind of level up from the actual engineering, but they have to go backwards and forwards as well. So if you give a specification to the engineering team that covers the whole bell curve, it's going to be a long and arduous.
You're never going to get there.
And someone's going to try and polish all forever. But if you can meet a minimum set of specifications, give that simplistic specifications to the engineering team, keep the engineering team on track. You know,
I think
they've got to hit that.
Because they'll end up deviating a bit, right?
Yeah. So they're going to say it's really cool, all that type of stuff. No, I need this. Does it do this? Yes. And the other part of it is technical debt. That's a talk for another time. But yes, if we can get there really fast and there is technical debt, then we can assess that technical debt as part of V2 or whatever. I think cost effectively comes down to probably limiting the scope, making sure that any engineering we do is going to have an outcome that goes towards the end result. And that end result has to cover the wide population, a wide part of the population of end users. There's many ways to skin the cat. This is stuff that we're seeing from different customers though. Like, talked to a couple of customers recently and they're like, oh, this young engineer's doing this. And I'm like, he's engineering himself a job.
I was about to say, yeah. I mean, it's because he's not managed.
Yeah.
You don't want to stunt their growth, you know, like you want to empower vision, but sometimes you have to just keep the lid on it and just focus on what we want to do. The cool stuff will happen. Will happen.
Yeah. You can, but
let's get this done first.
Yeah. But I think really good engineers, and this can be on record, but really good engineers are the ones that look forward and they say, this is really cool and I can see the application for that. So I'm making a business case for rolling that in so that it gives us this advantage later. But that, to me, in my experience, is few and far between. I think a lot of engineers...
It's like hit or miss.
A lot of engineers
do it
for their own purposes. Yeah. They do it for their own learning or something like that, where it really should always be in the best interest of the product or the company. And managing engineers is a challenge because engineers can polish forever. They've got to be given a brief. You've got to have an understanding of the art.
Right, so you have to know what they're doing in order to manage them.
Yeah. So getting an engineer, we've seen a lot of this lately, getting engineers directly out of university. Unfortunately, if you're trying to manage young engineers, you really need to know or have some idea of what the amount of effort is to get from point A to point B. And that's where maybe people like us or other businesses as a consultant could help with that sort of stuff. If you allow an engineer a certain amount of time, they'll just fill it. And they'll just fill it with work.
And if it's a team of engineers, it's like herding cats, you know, just trying to keep everybody in line.
Yeah. So knowing how much time is reasonable. So saying, okay, I think you can turn around this set of schematics in a week. They're going to go, oh, that's uncomfortable. I don't know about that. And then they're going to go, no, I think you can get it done in a week. I guarantee it's done in exactly a week. Right. And I think that circuit board, you can get that circuit board done in a week. Oh, it's really hard. It's going to get done in a week. But if you give them 2 weeks, it's going to get done in 2 weeks. Yeah. But it's a challenge that has to be overcome in a team environment. Yeah. I really don't believe that project managers who are not skilled in the art can really do a proper job for the business because, unfortunately, engineers are going to take the piss, right? And I've seen agile stand-ups, where everyone goes like, okay, this is this task. Everyone around the room, how many days is this going to take? And I'm like, that's a half an hour job for me. Okay, so all right, we're going around the room. That's 3 days. What the fuck are we doing? Why are we saying 3 days? This is a half an hour thing with the project manager.
But you can make that call because you've got the experience.
Yeah. So got to be really careful. And I think everyone's got to be on the same page. If the engineers are aligned with the purpose and the outcome, then it makes everything a lot easier. But the best way that I've seen to facilitate that is to have demos. And everyone's on the same page. You know, all engineers, all designers really want to be seeing their stuff be used, right? So, and everyone really wants to be...
It's like a legacy, right?
Absolutely, yeah. You're leaving your legacy. It's kind of that thing. If you get everyone on the same page with, okay, this is the demo. We're going to have MVP 1 where no smoke comes out and it's going to be on this day. And you've got your mechanical, electronics, firmware, software, app team, whatever. And everyone goes, oh, that's hard. Okay, yeah, I think we can do that together. Then there's that camaraderie. Then there's that challenge. And then there's that piece where that person's letting down others as well.
But I think it's about monitoring the process as well. And if you see it, diverging a little bit, I mean, adjust the goalposts.
Yep, absolutely.
Don't push someone that they have to get it done by exactly that time. But you need to have a good estimate of, have some tolerance.
Yeah. Yeah, so the other part of it is obviously technical debt is the other side. So if people aren't extending their time and they're getting things done quicker, great. Then they can, any technical debt that they've encountered, they can go and fix that sort of stuff. If they're trying to get things done quicker than what they really should, they will incur technical debt. And they might get something done, but they might say, okay, in the next sprint or the next phase, I have to go back and fix that thing because that's going to bite us in the ass. But in general, the best, most successful product development projects that I've been part of have negotiated timelines. All the stakeholders involved.
It's tracked.
It's tracked, absolutely. Yeah. But it's like, we are going to have P5 on this date, and those P5s are going to these test customers, and we're going to have P4 on this date. At this point in time, it's very hard to understand what the engineering work is involved. Do you think that's achievable? And we go, yeah, from our experience, I think that's achievable. That looks achievable. And then as you do it, you're getting that feedback. And the system the project management system goes green, green, green. Oh, we've gone to orange now. We've got a RAG system. Yeah. It's gone orange, but okay, now we're going to adjust the goalpost. And here's the real reasons behind it, not just that someone was in their own brain, just doing cool. Yeah. So yeah, you got to have those goalposts, and you've got to set the time limits, and you've got to have everyone on the same page and everyone collaborating, and everyone's got to be pretty well managed.
Got to say, you can't tell them the date and expect them to fulfill it. You have to guide them.
Yeah.
Some people might.
Yeah.
But if you're working in a team, you have to guide them.
Yeah. Yeah. Everyone has to be supported and part of the process. So. We're currently working on our very own data logging and control system, Cranio, to make it cheaper and easier for everyone to develop their own IoT solutions. This involved designing and manufacturing the Pro.io line of modular electronic devices. What was it like working on this project?
Yeah, so
this on my Pro.io.
This was the first one that I got thrown into. Mm-hmm. It was really interesting because I had started from, basic electronics and then migrated. And it's just amazing, the drive of an idea and making it happen. It's exactly the field that I'm familiar with, things talking to each other, high-speed communication, talking to the internet, displaying it onto onto a dashboard. It's really a familiar space for me.
Yeah.
So it was really exciting to get involved with it. Mm-hmm. The team actually, they did amazing jobs. There were all different modules that had to plug into each other mechanically, electrically. We had to interface between the firmware guys, the hardware guys, make sure the hardware is working before it goes to the firmware so that there's no backwards and forwards, save some time. And, things went really, really, really smoothly. I mean, Cranio's been around, a while now. And it's really got some good legs to grow. We've got that fundamental foundation of the product that is stable, web interaction, app interaction. It's really an amazing product.
I've always wanted to do easy IoT, sensing anything and automating everything. And I've found it hard, going into Arduino land, going into Raspberry Pi. You're doing electronics, so you have to be an electronics engineer of some sort to put together a circuit board. You can get your different modules from Adafruit, which is great, but you still then have to understand the electronics, and then you have to write the code. So you got to write firmware code in C, which is challenging. Arduino really makes that a lot easier. And then from there, you've got to go and interface with it somehow. So you can have LEDs or whatever, but a better interface is probably a phone app or a web app. So it's three engineers at least, mechanical, electronics, maybe electronics can do the firmware, and a software guy to be able to make the app or whatever. Over so many years, this has just been a personal challenge of mine to be able to get to a point where we can easily spin up an electronics widget that robustly does what it needs to do. Sensors with any interface or any industrial sensor off the shelf, and an actuator.
But a consumer product, not an engineering product. You buy something off the shelf, it connects, and it's an easy process to get this device online, logging the data.
So, but that's been a massive challenge, and so I sort of started doing electronics back in 2012, and I was doing it hardcore for about 4 or 5 years. And a lot of the learnings that we made there was kind of the basis of a lot of the Cranio things. Sam was the one who said in 2018, can we not do any more code that is 3 different projects at once in parallel that have all got different code on them? And
there's a lot of overlap, right?
Yeah, absolutely. They're all trying to do similar things. One of them's trying to work with an app. One of them's trying to send information to the back end and to a dashboard. And one of them's just an electronics widget. So why can't we do it in a way that's consistent? So that's been the main challenge. In regards to the electronics on Cranio, for us, it's just being able to interface with any sensor. And we've kind of covered them all now in the same way that all the PLCs and things like that. We've kind of looked at what PLCs do and, way we interface with different things. We've covered all those things. We've had to go through all of the engineering to interface with 4 to 20 milliamps, 0 to 5 volts, 0 to 10 volts.
You've got stepper drivers there. You've got
motor controllers.
You've got anything you can think of. You can plug into the Cranio. Yeah. It'll digest it. It'll digest it and display it on a dashboard. If it's over LoRa, if it's over Bluetooth, choose your technology that you want to use.
Yeah. When you've come into it, we've gone through a lot of these hardships with the actual core of it would be the microcontrollers and understanding which microcontrollers we like to work with in the ecosystem. Then once we've got that down, the core sort of firmware, the core interactions, then we've got different analog front ends, digital front ends. Power management's a big one because especially during COVID, my love of TI was just non-existent. All those components that I was using, I think were, they were the main components that were going into the automotive industry. And the automotive industry said, well, we can't stop selling cars. So they just bought up all the components.
And if they said no to an automotive industry, they really can't make. They just can't make it.
So we had to redesign all that. So a lot of the new power management systems have come from specific suppliers. There's been so much iteration, so much maturity in all of those subsystems that are in that huge library that now when we want to come up with a new circuit board that fits into a form factor, the Cranio form factor is basically to eliminate cabinets. To eliminate weatherproof cabinets. We're making a little micro cabinet without glands. We're just using those little silicone seals and the cable wedges and stuff. And that's an idea that I've had, riding my bike or, in my own boredom space that I want to do. But we have that form factor, and then whatever we need to interface with, we just drop it into that form factor. And we bring those subsystems that we already know. So to do things right, in my opinion, is to reuse the assets we've got and iterate on them and extend on them. And I think you've kind of seen the result of that.
But also to manage the full product from the mechanical, we even do the enclosure, CNCing here. It's a one-stop shop for everything. So it's going to be a good product.
Yeah, we hope so.
Yeah.
But it's different to, so again, this comes back to my core purpose, I guess. I've always been the engineer who goes and does the product design and then helps to implement the product design on the production line. And I've done that up in China originally, done a lot of it in America, and now I've done a lot of it in Taiwan as well. My real passion is, why can't we do it here? Because Taiwan, for instance, they've got a pretty high cost of living. I think I have to check this, but I think their cost of living is somewhat higher than ours in some of these places. Why can't we do it? Yeah. Doing things here in-house is kind of, first of all, it gives us the ability to turn around prototype designs faster than anywhere else in the world. Secondly is, let's learn those processes so we can understand them better as an engineering company and we can design better to the manufacturing process. And thirdly, let's use our machines to actually manufacture some stuff. So we'll see where we end up. But we know that the Cranio Pro IO design is going to go out there. We've got some trials happening now with that. And we can pivot it to within that same form factor and within the ecosystem really fast. So that circuit board, we can just drop on the different subsystems that we have, build a new subsystem which might be specific to some sensing or things like that, and then have the system speak that same language all the way through the ecosystem.
It's future-proof.
Yeah.
Because if there's some sensor that comes out, then it's easy just to build it put it on the stack and it just talks.
Yeah. The other thing that we're seeing lately, which I had a discussion with this week with a colleague, was automation. So AI is amazing now, and everyone's doing all this new application work where they're applying these AI or whatever, but the interface to the physical is still the challenge. So back 10, 15 years ago when I was trying to just get sensor data and then having to go down into Arduino land and things like that, that is still a challenge now, and it's probably more a challenge than ever because we've got so much smarts happening here in software, but we're not currently able to easily and robustly interface with the physical. So if we can be the provider of the modules that have a specific way of doing things, they all speak the same language, expose that to the controller, and then robustly and reliably provide that service as a widget, then we've got a place. Yeah, so I'm glad that you had a good experience with the Pro I/O.
It's really good.
We work closely between Altium and SOLIDWORKS. So one of the things that has helped speed up this process is that we'll be coming up with a mechanical design which we think is going to be the right fit for the user experience, and then we just give you a circuit board shape, give the electronics team a circuit board shape.
The speed between the electronics and the mech, they're in the same space.
Absolutely.
Like it's easy. I remember with the GPS puck, for example, we were designing the new puck. I mean, it was so quick. Get the PCB design, talk to the mech guys. We need to adjust this. They do the adjustment. They push it back to Altium. It's there ready for the electronic guys to now put in a new connector. They know exactly the space that they've got. Could we move it up a little bit because this component is in the way? In a few days between having everything in one place.
The big thing there for me has been this SOLIDWORKS Altium interconnect co-designer, I think they call it. So there was a time back, say 2014, where I was bringing in step files. So you'd make the mechanical design in SOLIDWORKS and you put your circuit board in there, you give your circuit board layout. You'd then bring that into Altium, and then Altium would have the circuit board shape. You'd place all your components and you'd output that as a step file. You'd bring that into your SOLIDWORKS. It's not a long process, but this just makes it a seamless process.
It's just seamless.
The next level as well is that anything that you move in either one of those things can somewhat live interact with the other one. So you basically do it in SOLIDWORKS, give the board shape to Altium. Altium, you start laying out the different components. You push that back and all of a sudden the components just appear. So SOLIDWORKS actually, the add-in actually creates the components in a SOLIDWORKS native way. And then in SOLIDWORKS, you can grab that component and move it, and it will move it in Altium. So you're no longer are you having step files and revision issues and things backwards and forwards. It's really, really fast. There was a time where it was broken. About a year ago, it just didn't work. We went back to step files or whatever. But the latest versions have just gone ahead leaps and bounds. That tool chain has really helped us.
It's reducing time because now by the time you've got your PC board, built the PC board and put it in the enclosure and realize that you've got a capacitor that's touching the edge. Go back, design, remake.
Here we've got the Altium 3D interaction.
Yeah, so this has all the components. We went through this a bit earlier, but it has the enclosure, it has the height, the exact step file of the components. So you know exactly that these things are going to fit. You got where everything is going in. And those components you can't actually go wrong if you've designed everything correctly because you're going to get it right the first time.
So those components there in particular, so say the USB-C and the SD card, they have to be to the 0.1, 0.2 of a millimeter. Otherwise, that silicone flap is not going to see
exactly because this is IP rated. So.
And this is important having, especially a consumer product that can operate in a consumer environment. Consumers are the hardest users to satisfy because they will abuse the thing to the absolute max, and secondly, they will demand the absolute lowest cost and the most.
So you got to get it right. You have to get it right,
absolutely,
with as few iterations as possible.
Old Lenovo is
taking strain.
It's struggling a little bit. This is most up-spec'd Lenovo you've ever seen.
It's got dedicated graphics.
Yeah, dedicated graphics and all, and it's got more RAM and all that type of stuff. It's an older one, but does the job. Still using 2023 because I know that there's no bugs. 2024, I'm just scared of going up.
You know the bugs.
Oh, the bugs, yeah. Every time you go up, you're like, how much effort is this going to take me? Dan and I were talking last time on the podcast, like 2014 was like the peak of SOLIDWORKS. And on the old computers that worked so well, like it worked so well, you go to like 2024 and you're like, why is this the same speed? Why is this like, I've got the latest and greatest, this thing is 10 times faster than 10 years ago. Anyway, so this is the full stack up model, and this is the module that we were talking about there before. So we've basically got the whole model with all the different parts, but the circuit board comes in as a subassembly. SOLIDWORKS and Altium use this. There's a SOLIDWORKS Altium interconnect. It basically builds the circuit board using native SOLIDWORKS elements. So it builds a circuit board and then it builds each one of the little components using, extrude features and things like that. I think it also brings in the step files. So say the step files of these particular components, the different headers, like you can see, Phoenix contact.
Down to the label.
Yeah. So it actually builds it in there. And then once you have bought it in from, say, Altium, if I was to push any of these components left or right, I can then use the Altium interconnect to basically push that update to Altium. And we've done that before. We actually did that at the very start with these, Pro I/O stacking things. It's pretty seamless now, and it makes a lot of sense to do it this way. It's a pain in the ass when it's broken. It was broken for a while.
And when you depend on it, it's pretty important.
Yeah. But you can always go back to step files and things like that. I started off in Eagle. Now Eagle is not the open source Eagle that it was. And then I went on to Altium pretty early on. Now we've got sort of 3 perpetual licenses, and they're always sort of booked out by the team and always being used. So this works in really nice with SOLIDWORKS. There's obviously many other programs that people use. I like the idea of KiCad. I love the idea of open source engineering tools, primarily because you know that those tools are always going to get better.
But there's an easier entry point for beginners.
Yeah.
Because it's free, a lot more people are going to be using it.
Yeah.
There's a lot more people asking questions, a lot more contributing to it.
Yeah.
So, I mean, there's so many tools that are built on top of KiCad.
Yeah, absolutely.
I found that you can take a PCB, upload it or create it in KiCad. It generates the enclosure for you with the little bushings and and everything. It was quite a cool plugin.
Open source,
and you 3D print it, and you're done. You know?
So open source engineering, I think, is the democratization of engineering, and it levels the playing field because we pay for Altium, and it's actually not that expensive. And when I was looking at it compared to the other industry standard ones at the time, it was nearly an order of magnitude cheaper at the time.
It's become the standard.
It has become the standard for sure. And I think it's because of that. It's highly featured. It continues every year to get better. It is actually growing and always improving. And the bugs seem to get squashed. And it's just an amazing thing to work with. But if you don't have the money to interface with it, I think you can get free, or you can use the free version, CircuitWorks or Circuit Maker. I can't remember what it is. But you can also use all the open source stuff. And KiCad is an amazing tool that can get people into electronics and doing things. But electronics shouldn't be scary. For me, as a mechanical engineer, it is scary because you can't see it, right? Yeah. And you can't touch it and feel it. But, if you've got the right oscilloscope and you've got different modules that you've worked with and you understand
if you look at a PCB and you actually understand that each one of those things on there has a function, it's easier for you to understand what's going on. If you just look at a board and you just see components,
no.
But when you drill down and, as engineers, you can already make out just by the shape or how something has been laid out, this is definitely a power supply. There's some filtering here. This is all a matching circuit.
Did you annoy your parents by pulling everything apart and pulling all the...
My mom always used to make a joke that, like, for my, must be my 10th or 12th birthday, my father bought me an old school TV or a tape recorder, and I would just disassemble it. There you take out the screws. You had all of these. I mean, everything was not done electronically back then. You had little pulleys, you had little chains. Giving you timing. I mean, I think of the journey that I've gone through my dad's involvement. I knew. Wish that it could happen now. But now people are starting on a different level.
Yes.
They don't have the concept of where did things come from. Even from a software point of view, people are writing high level languages.
Yes.
They don't know what's really going on underneath in the MCU, and you can only have that concept when you've actually started from assembler level. But that's not going to happen, unfortunately.
I think it can, but it's got to be an active experience. You know what I mean? Like, I think my journey has been start off at a high level. I love
we've gone from both ends and met in the middle.
And I've sort of stepped away from it. So I love the little Dick Smith electronic stuff. Then being relatively good at through university at the things that I did with electronics, I started off at Arduino level, and then sort of, as we wanted more and more functionality, we found the limitations of Arduino. Then we went into the MP Lab or Atmel Studio at the time. We found the limitations of that, and then we went into our own things. But I've brought in other people like Sam who can do those things for us. But the electronic side for me has been just out of a necessity. I need to make this thing with these electronics modules or these whatever fit into that thing, and you're banging your head against the wall. I've kind of come down to a certain level, but I don't understand the absolute first principles of a lot of stuff. But as engineers, I think there's a balancing act. Do you need to understand the first principles, or do you just take it for granted and use it?
You're starting at a high level.
Yeah. So, but I think there's always a benefit to understanding as low a level as you possibly can. To be a proper professional, an industry-leading professional in that part of the domain, I think you got to do that. But that's also a bit of a trap, I guess, if you niche yourself into that sort of domain. So I've seen many software engineers in particular sort of jump between one thing and another, and they're all high-level languages. And they sort of go, I've done front end, I've done back end. I really now want to do firmware. And it's like, well, have you really done front end? Have you really done back end? Did you really contribute to the React libraries?
Did you just copy from Stack Exchange?
Yeah. So anyone who is going to be a lifelong contributor, they will be someone who has gone into the first principles, and then they're starting to progress. And my personal opinion is that every engineer through their career should be a domain expert in at least one domain.
You can't be an expert in everything.
No, but you should be really, really, really good and state of the art or pushing the state of the art in at least one. And then from there, once you've done that, then the surrounding domains that you may interface with, go and get good at those. Because then you can actually provide information back. Or
also, don't assume that you'll know everything.
Yeah.
Like you'll find that you're working on a project and a junior will say something, and you're like,
that's kind of the
never assume that you know everything.
Yeah. Well, that's the beauty of engineering, right? Like you're always learning, and hopefully you're learning a lot from the peers around you. If you're not learning from the peers around you, then maybe you're not in the right place. Yeah. Cranio has been a long process. We've still got a long way to go, but the Cranio Pro ecosystem is there, and it's very fast for us to get things out now. And if we want to interface with a new sensor or actuator, come up with a new subsystem, we make a board. We hardly ever make Franken modules these days. We just kind of make a board, and
it's really easy these days. And there's little that can go wrong if you've done the schematic properly, if you've done the component. Matching everything up.
Yep, using reference design,
going through everything that we've gone through. There's little that can go wrong.
Yep.
When you apply power, there should be no smoke.
Yeah.
Unless there's something mechanically wrong, a blob of solder that's sitting on somewhere, or a component that's the wrong way around, or someone has turned the microprocessor as well. There's not too much smoke that should be coming out these days.
Yeah, we'll see. It'll be good to continue on and trying to finally get this thing to market. But I think there's also things we can do in the middle as well, which is using that IP library that we've got and allowing people to come to us and say, hey, like you've got that motor driver, closed loop motor driver system, and I've got these industrial sensors.
It's all building blocks.
Drop it on a board and put it in a Deutsch box, or put it on a circuit board that we put into a cabinet, and bang, we're done. That's all for today. Thanks to everyone listening in. Feel free to like, subscribe, and leave a review. Have your say. Hot takes are very welcome. Until next time, make it good, make it fast. See you soon.